Hi, this is Dan Spurlock from PFC Pro, and we're going to do a very brief demonstration here on our power factor correction testing. You can see here we have a standard single-phase motor, but we have simulated three-phase by putting 3 of the alligator clamps on so that we can simulate a three-phase testing, and we have the 3 CT clamps. This motor is hooked up to a hydraulic pump so that we can actually put it under load, and it's all hooked up to our standard testing kit, which is going to be, we're going to demonstrate for you how quickly that it does test and how accurately. Over here on this side we have our actual PFC correction unit for power factor correction. We're going to do a before and after test, and here's a standard kilowatt meter that's going to show you some real numbers in real live time. So I'm going to go ahead and put this under load or under energy with the motor, and if you step up here, if you look here, you can see some of our numbers. There's the voltage. We're going to take it to, there's our hertz, in this case 60 hertz, but we can do 50 hertz. There's the power factor of this motor now, right around 31 power factor. It is not under load. That's standard. When it's not under load, it's under low power factor. We want to put it under load. So we're going to step up here and put it under load, take it up to, let's do about 150 on the PSI, which puts it under load. Now, back here you can see how that changed the number from a power factor of 31 to a power factor of 54. Over here on our test kit, we have entered the data for the motor. We put information about the specific motor in. Let's say it's pump number 3. We can test for a cross-the-line starter, or we can do a step-up starter or a Y-start delta run. Information on what the motor does, in this case the water pump. I like to put in some additional remarks such as what is the horsepower of the motor, how far the motor is from the panel, because that gives us a little additional information on possibly saving even more money. We have here a plastic type unit, which is what we have with this on this test. And this just gives data on the wiring and how long the motor runs. Everything is hooked up and ready to go. It's just a very quick start. We hit next, and a reading comes out on our computer of where we are now. Remember, it was 54 power factor over there. Here it's 53, 54 power factor. Always fluctuates a tiny bit. 6.4 amps. We're ready to do the test. Here we go. We're testing. And we are done. The test is now complete. At this particular point, we simply get a label over here. This label gives us some of the specific information that we want on the motor and tells us exactly what kind of unit we need to build, so that we can actually get all the data that we need to build the specific correction unit. The person who's doing the testing takes the label off, sticks it on the motor, and he's done and ready to go on to the next motor. Now, testing normally takes 4 to 12 hours. As you can see, we've completed it in less than 2 minutes, and the testing is done. Now, let's try something. Our unit, I'm going to step back here and turn our unit on, check those numbers, and you can see them go up as we turn our correction unit on the power factor. It's on. Power factor just jumped to 97. That is our correction unit. Most power factors should be 95 to 99, and we did it that quickly. This unit is designed to be built very quickly, almost on the spot if necessary. The test is very quick, can be done in a matter of 2 minutes rather than 4 to 12 hours. A very efficient way of testing power factor and correcting for power factor and saving money. You can see the amps dropped from 6.4 to 3.3. That is proof right there that you're going to be doing some savings on your electric bill because of less energy, and you're going to eliminate power factor penalties. There's our voltage. Our voltage didn't change. It stayed the same. And our kW stays the same on the motor, which is what you want it to do. The motor should never change on the kW, and we never change it. Very quick, very efficient, and very accurate. Remember I said that we actually put the label on the motor once we get the data collected after we do the testing itself. That's so that after we build the unit, the installer can go back, match up the unit, which will have the same label on it, with the motor and install it very quickly. And the other thing is the reason we do this process is because once the test is completed, all this data that we got in the computer from that quick test that took just a matter of a few seconds basically, is transported back to our headquarters. All that data is put together and we are actually able to build a unit from that data. Now what's also interesting is the standard power factor correction unit, because of the nature of what's inside of it, can take anywhere from 7 to 10 hours to build. We can do it in less than 60 seconds. We've actually run tests on it and timed it, and we build a power factor correction unit in less than 60 seconds. So you're looking at a turnaround time of far, far greater than what's standard in the industry. Most of the time, the customer will have to wait anywhere from 2, 3, 4, sometimes up to 6 and 12 weeks before he gets his power factor correction unit. We can turn it around and have it back to him in a much quicker time, matter of just an hour or two, or if we can, actually we can build it on site and do it in a matter of seconds. But before we finish, I'd like to show you one more thing. This is just kind of a quick rundown on what we're talking about with power factor correction. You can see this is a standard power triangle, and this represents the energy that comes into or is used by a standard inductive motor. A motor will need to use the watts, and in this case we call it kilowatts. But because of the nature of induction, it's going to produce its own power, its own electromagnetic field that is a reactionary to the induction. That energy we call amps reactive, volt amps reactive, or essentially kilovolt amps reactive. That is wasted power. It is not used by the motor. It goes back down the line and is sent back towards the panel or towards the power company. The power company therefore has to send volts amps to enough to overcome that kVAR that's going back down the line that's fighting it, to overcome that and still give the motor what it needs for kW, or the watts, or the kilowatts itself. On power factor correction, we actually can come in and reduce the kVAR, reduce that wasted energy by recycling it back to the motor. The result is the power company will send us less, will need to send us less kVA or volts amps. There's where the money can be saved. They're sending less energy to overcome the wasted energy. Many times on an electric bill it will appear as power factor penalties or kVAR charges or kVA charges. And what we want to do is to reduce the kVAR itself, and that's exactly what we do with power factor correction. Simply take the wasted energy, instead of sending it back down the line like it normally does, we literally recycle it back to the motor itself, so the power company sends you less power. And we do that whole process by not changing the kW or the kilowatts, because the motor needs to have the same watts. That essentially is a very basic explanation of power factor and power factor correction. So thank you very much for joining us on this particular demonstration on power factor testing and power factor correction.